Hello AP, welcome back. We got 5.3. We have a new term, a very important term called enthalpy. How does energy, enthalpy, and heat relate with each other? Well, we sometimes use each of them interchangeably, and what we mean by that is because energy, enthalpy, and heat, these are all forms of energy. They're just different types of energy. So I know it gets a little confusing, but with each one of these, they are energy, but they're measuring something different. So let's go through each one specifically. Energy, the capacity to do work, which we already know that, and transfer heat. That's where the first law of thermodynamics comes in, where delta E, and we call delta E change. Remember, change in energy. You can also call it internal energy. The change in energy equals heat plus work. Okay, which we know Q and W by now. When we measure all of these, we want the units to be in joules, and you can use kilojoules too. Okay, but it's correlating work and heat at the same time. Whereas heat alone is only looking at the transfer of energy when you have a difference in temperature. So when temperature changes, and we call that delta T, okay? So when you have a final value versus initial value, how did that temperature change? If it gained heat, we call that endothermic. So this would be gaining heat. If it lost heat, we call it exothermic. So negative Q. So positive Q versus negative Q. So remember when we were looking at a system versus surrounding. Depending on if the heat went into the system from the surrounding or vice versa, we used arrows. So if it was endothermic, we would see the arrow coming into the system. If it was exothermic, we would see the arrow coming out of the system. But no matter what, heat always flows from warmer objects to colder objects, okay? Remember, think of the hot coffee versus your hands. Okay, your hands are warming up because the hot coffee is transferring that heat to your hands. Enthalpy is another way that we can measure heat, but there's a little twist to this one. It's got to be a constant pressure, okay, which means pressure cannot be changing. So you would not see like something called a delta P, like a change in pressure. You wouldn't see that. So this has to be a specific value, whether it's an ATM, torr, mmHg, it doesn't matter what unit, just as long as pressure doesn't change. But notice we're still measuring heat. So with enthalpy and heat, they are related to each other. Okay? So in many chemical reactions, whether you have a physical change, so phase changes, or if you have a chemical reaction, most of the time, if you notice when we do labs, we don't change pressure. Pressure is constant. So whatever the pressure is in the room, that's just what the pressure is. We cannot, this is the kind of but part to it, we can't measure enthalpy directly, but we can measure how it changes. And that's how it's related to heat, because we're going to look at how temperature changed it. Okay, so we can measure delta H, we can measure the final and the initial values, which you're going to see this pop up when we get to the very last video in this chapter 5.7, how we're going to take final minus initial. But using the first law of thermodynamics, there is an equation we can correlate enthalpy, heat, and energy. Okay, so how do all three of these correlate together in an equation? Well, it's right here. So you have delta H, we have the change in enthalpy, we have the change in energy, we have P, and notice that P does not have a triangle next to it. That means P is constant, so it's not changing. But then you have delta V, and we already know capital V is volume, which means change in volume. So if the problem mentions something about changing in volume, regardless, anytime you have a triangle, you take the final minus the initial value. But there's a little twist to it. Okay, this is where it becomes really cool. This part right here, P delta V, if you look right here, how does it correlate to work? Well, work equals the negative P delta V. So if I show this correlation, P delta V, this part right here equals negative W, okay? So notice right here I said W equals negative P delta V. Well, what if I have positive P delta V? That means it's negative W. It just means that the negative went to the other side, okay? E, according to the first law of thermodynamics, is Q plus W. So if I substitute that in here, this is what we call deriving an equation. How does this equation turn into something else, okay, which we call also substitution. So if I use the first law of thermodynamics and I plug it into Q plus W, well, notice what happens. W is the same value. You have W minus W. Well, W minus W just becomes 0. So Q plus 0 equals delta H. Well, the only way that delta H equaled Q is as long as you had pressure constant. Okay? So notice I didn't have to know anything about a pressure value. I didn't need to know anything about volumes values. I just know that P delta V equals negative W. And then you get a very simple equation called delta H equals Q. Now, we put this little P right next to it to signify constant pressure. So how do all three of these correlate into each other? Well, if I know what energy is doing, Q and W, and if I know what heat's doing, then I can take energy, heat, and work, and I can figure out what enthalpy is doing. We call it the change in enthalpy. Now, enthalpy and heat go hand in hand. So if you have a positive delta H value, it's endothermic. Same thing if Q was positive. That means the heat is transferred from the surroundings to the system. So you would actually see the Q, the heat, coming in. If delta H is negative, we have exothermic, and we know our Q would be negative. Heat is transferred from the system to the surroundings. So if you know what heat is doing, you know what delta H is doing because it's the same value, just as long as you're at constant pressure, okay? So all of these values have another relationship to it. The change in enthalpy, the change in pressure, change in volume. There's all called something called a state function. What a state function is we can't measure H, P, and V just at one specific state. We got to see how it changes because it's a reaction, or it could be a physical change. So what a state function is, it depends only on the initial value and the final value of the system, not how it changed, as in it doesn't matter what the pathway is. So we don't need to know, did it go into the system or surroundings? Okay, we don't need that info. We only need two values. We need to know how it started and how it ended. Okay, so an example of this, what do I mean by the pathway? The pathway is how it actually got there. So let's say we take a trip and we want to see what the difference is between Denver versus Chicago. If we start in Denver and we go to Chicago, well, the altitude is a state function, okay? Now, it doesn't depend on whether you fly, drive, or whatever. Only the elevation of the two matter. You still got to Chicago. Whether you flew, you got there faster. Whether you drove, you got there slower. But you got to see a whole bunch of states as you went through your travels. But you started in Denver, and you still got to Chicago. Initial and final, okay? You leave my classroom to go to the next period, period 2. How did you get there? Did you go down the stairs on the north side? Did you go on the stairs on the south side? Did you go to the restroom first? Did you go talk to your homie first? Did you loop around the R building to go find whoever you needed to go talk to before you got to class? You all got to period 2, just some of you got there faster. Initial versus final. So what a state function is, all of these that you see with triangles, they're all state functions because it doesn't depend how the change occurred. All we need is initial and final. So does not depend on the path. So what we mean by the pathway is like system versus surrounding. The problem is work and heat are not a state function. We actually need to know, did it go into the system or did it come out of the system? So work and heat are not a state function. We actually need to know what's happening there. So in conclusion, because we're going to practice these equations in class, okay? If you look closer at energy, first law of thermodynamics says Q plus W and delta H plus delta E P delta V. We already know what happens at constant pressure, okay? We already derived that right above. Q equals delta H. But what if it's constant volume? So look at this equation, okay? If you have constant volume, that means your initial and your final values, they're the same value. What's the same value minus the same value? Well, we call that 0, okay? So notice this part right here, it's going to be 0. And what's 0 times pressure? Even if it was 1 atm, what is 1 times 0? Well, that means this whole value disappears because a 0 times any number is just going to become 0. So what do you have? That means you have delta H equals delta E. And we know that delta E equals Q plus W. So you have to pay attention. Are you at a constant pressure or are you at a constant volume? This one we're going to use the most, especially when we get to the lab part of this. In chapter 5.5, calorimetry, it has to be at constant pressure. So this is the one you're going to see probably 99% of the time, but I still have to teach you all the ways. Okay? See you on the next one.